So we're going to start talking about hydrogen finally. This is going to be what we are talking about, the hydrogen and the hydrogen-like wave functions and how we can build hydrogen into new things is going to be what we talk about for the rest of the quarter. So this is why it's such a pivotal day, is because this is going to start to define what we do for the rest of the quarter, which is pretty exciting. I'm going to get something set up for that as well. Whoa. Okay. I don't know if that... Oh, no, that's not going to do what I want. Okay. I got to do that. Okay, so the equation, I'm going to write down the equation that we're really going to use most of the time, and then we're going to write down the equation we have to get through to get to this equation. It's kind of important to do this in 2 steps. But again, I'm giving you the short story first, and then we'll get through the long story. The Hamiltonian that we are going to be most interested in is negative h bar squared over 2 mass of electron, del squared for the electron, minus z e squared over 4 pi epsilon naught 1 on r. This is the motion of the electron around the nucleus. This is the attraction of the electron to the nucleus. And you should instantly ask a very important question. Where's the nucleus? Right? So this equation is already a simplification of what's actually going on. What's actually going on is we really do need to think about the nucleus. And we have to think about some electron that's some distance away from the nucleus. And technically, the nucleus and the electron can both be moving. So if we wanted to write this down, rather than writing it down in the already simplified version, if we wanted to write it down in terms of the 3 coordinate components of the nucleus moving and the 3 coordinate components of the electron moving, we actually need a second kinetic energy term, and our radius should be this relative distance between the two. So if we write that down, this is the more realistic, well, we'll see why we get to simplify this, and it's actually a pretty important simplification. Mass of electron, h bar squared, sorry, I forgot 2 there. 2 mass of electron, del squared for the electron, plus, I know I've got a plus minus, but h bar squared over 2 mass nucleus, del squared for the nucleus, minus q1, q2 over 4 pi epsilon naught 1 over absolute value r nuke minus r electron. And those would be 3-dimensional vectors inside of there, right? Because it could be moving in 3-dimensional space. But we can simplify a couple things here. The first thing, if it seems weird that we've got the ze squared, the first thing we can remember is that the charge of the nucleus, the charge of protons, is equal to but opposite of electrons. So the charge on this nucleus can be thought of as a positive z charge of electron. The charge on this electron can be thought of as negative charge of electron. So that's where we get the ze squared. The negative sign is kind of taken into account in the fact that we're subtracting this. In all actuality, when we look at the Coulomb force, we inherently take into account whether it's attractive or repulsive. This is going to be an attractive force. The 4 pi epsilon naught, that's just a constant of space. We're not going to worry about that too much. And then we can look at this r nuke minus r electron. And that is essentially just going to be, if we looked at it in terms of this magnitude, we can just define like a new r from that distance. That difference in distance can be r. The thing we haven't been able to get rid of yet is this term here. So we can explain all of that away. But this term, the nuclear motion, that one's a little bit more difficult, right? And we can think about this in terms of if we're going to this R, this position that's kind of relative between the two, we can think about how we're going to change del to be relative to the positions between the two. And we can think about how we could get a reduced mass between the two. Yeah?
So with the last term, 1 over our electron,
Yeah.
are
Those are vectors on top, right? So that's defining the three-dimensional space.
okay. So is that from like an arbitrary reference point?
Yeah, so we define a reference point, and all that really matters is not where the reference point is, but the difference between the two. If we tried to combine these two to kind of make sense of this term, we're essentially going to end up with a reduced mass term. And we can say, and there's a lot of hand waving that happens here. What we're doing here is the Born-Oppenheimer approximation. Oppenheimer, remembering the name of this approximation is how I can always remember who was the lead scientist on the nuclear project, the Manhattan Project, for creating the first nuclear bomb. It was Oppenheimer. Before he did that, he was a brilliant scientist that worked on quantum mechanics and nuclear motion. Essentially what the Born-Oppenheimer approximation says is if mass, well, not proton, if the mass of the nucleus is much greater than mass of electron, if the mass of the nucleus is much greater than the mass of the electron, you can ignore the motion of the nucleus. And that's an oversimplification of this approximation. This is what allows us to kind of ignore that motion. And this is going to be a problem, right? If we ignore the motion of the nucleus, we're going to have a couple hiccups. One, if you're ignoring the motion of the nucleus, you can't have vibrational motion in an atom or in a molecule, right? If the nuclei aren't moving, the distance between them is fixed, and you never get vibrations. If the nuclei aren't moving, you'll never get rotation either. But we have to keep in mind, it's not just the nuclei aren't moving, it's the nuclei are not moving relative to the electrons around them. There's all kinds of silly ways that people try to make a classical analogy of this. I'll give you a couple. One is if you think about a semi-truck with a bunch of motorcycles going around it, they just move around the truck, and relative to them, the motorcycles are moving much faster. Another one that is, I think, a little bit better, not better, it's one that's really common in Davis, is if you imagine a cow walking with a bunch of flies around it, the flies are always in the same position relative to the cow, even though the cow's moving. Right? So the fact that the cow's moving doesn't matter to the flies. In this sense, the nucleus would be the cow, and the electrons would be the flies just buzzing around. And it has to do with this difference in mass between the nucleus and the electron. The other way that we can think about this, and the way that I like to think about this, is to say that we're essentially going to break up the different energetic parts of what's happening with an electron around a nucleus. And we can think about the total energy. The total energy would be any of the energy from the electronic interaction. That would be that equation up there in black. That's just assuming the nucleus isn't moving, just looking at the electronic part. Plus, it would be the energy associated with vibrational motion. That would say the nuclei are moving a little bit. They have some slight displacement. Plus the energy associated with rotation. That would say the nuclei are actually moving a lot. They're spinning through three-dimensional space while they're also vibrating. Plus any energy associated with the nucleus. And that would be the last term. And what's nice is this is actually going to very interestingly, break up into our different types of spectroscopy that we do. Uh, electronic spectroscopy would be where we look at UV vis. That's our UV visible spectroscopy. The vibrational spectroscopy, that's our IR. Rotational is microwave. And the nucleus, this is NMR. And it's in the radio wave area. So the thing that really allows us to do this, that allows us to do the Born-Oppenheimer approximation, is not just the mass difference, but the fact that the energies of each of these interactions is going to be essentially an order of magnitude or several orders of magnitude different from each other. The electronic energies are going to be the strongest. They're going to have the biggest energy associated with them when we look at those transitions. Vibrational, and we can just look at that in terms of the energy associated with the different parts of the electromagnetic spectrum. UV vis is going to be higher energy than IR. IR is higher energy than microwaves higher energy than radio wave. So we can start to break up which thing we're concerned about, which thing we're looking at, based on the energetics of these interactions. So we've already done vibrational, we've already done rotational, nuclear interactions, NMR, that's for a different class. So we really want to focus in on this electronic part, looking at the electronic interactions. So that means I'm going to erase everything back up to that equation that I said was the important one, the one in black at the top of the board. So that means with the Born-Oppenheimer approximation, we have to solve this thing. Our R is the distance from the nucleus to the electron. Our del is going to be the part that tells us what's happening with the motion of the electron. And given the fact that the Coulomb force is 1 over R, it's a radial dependent, so anywhere in your theta phi, as long as the distance changes, that's going to be the important part. It's going to be easier to do this in spherical coordinates instead of XYZ coordinates. So we're going to look at this in terms of its full expression in spherical coordinates. We have negative h bar squared over 2. We should still use reduced mass, mass of electron versus mass of nucleus. It will approximately be the mass of the electron as long as the nucleus is large. So this will still be approximately the mass of the electron. 1 on r squared. Okay, here we go. D by dr, r squared, d by dr on psi, plus 1 over sine theta, d by d theta, sine theta, d by d theta of psi, plus 1 over sine squared theta, d by d phi squared psi. Minus this term, just that term, right? This is all just del, right? With this r squared, that all is just del squared. We did that last time, right? So this part, it might, remember when we did rotational, the rotational part last time, and we had essentially just this chunk? Now we're also going to say the radius can vary as well. But that's nice, because we already solved this chunk. If you remember, this chunk is what we called lambda squared. That was that part of it. We still need this minus part here, the ze squared over 4 pi epsilon naught, 1 on r psi. We still need that Coulombic attraction to talk about the electron being pulled towards the nucleus. So we can recognize a couple things. already solved this chunk of it. We've already done the rotational parts. That's where we got that cosine theta, that 3 minus cosine theta squared. That's what we did last time. So we can essentially say separation of variables is going to be a thing again. And we're actually going to do separation of variables in kind of a couple steps. So the way that we're going to think about this, or the way I like to think about it, and I hope this works for you as well, is we're going to define our psi of r, theta, and phi in terms of 3 parts. It's going to have some big function r that depends on r. It's going to have some function capital theta that depends on theta. And it's going to have some function capital phi that depends on phi. And each time we separate the variables, we end up with a constant. Right? If you remember last time, when we separated theta and phi, we ended up with an L and we ended up with an M sub L. The same thing is going to happen here. When we separate the r from the theta phi part, we're going to get some n value. And when we separate the theta and phi part, we're going to get some n value that's going to be related to like the L value of all of these. And when I separate the theta and phi part, I'm going to get some M sub L that's also related to that. So, step 1. So, and remember the theta phi part together, last time we called that y of theta and phi. So we're going to get 2 things when we do our first separation. We're going to get some n value when we solve this r part, which, again, we're just going to take answers. We're not going to develop answers. We're going to get some n value from that. And then when we look at this, we're going to say the constant r is going to have to be, the constant from r is going to be related to the theta phi constant. So we're going to get some conditions on our L value from that. N and L are inherently related to each other because we're doing separation of variables. And then 2. This one, that's just how I draw a capital theta. So, because I have to like denote capital theta from like lowercase theta. So that just happens to be how I draw capital theta. Mock me when I'm not making a video. If you're planning on mocking me for that. So, we're going to separate theta from phi. And we're going to get restrictions on M sub L. So we're going to have this nice kind of cascading effect of which part we separate and how we say those energies need to be related to each other and what that gives us in terms of our counting variables. So I'll write that out in 2 parts here for you. Back to black. We're going to have one part that's 1 over y times negative h bar squared over 2m. Sorry, 2 mu, reduced mass. Again, approximately equal to the mass of electron. Eta squared y is equal to a constant. Similarly, this part looks a little ugly, but it's not that. Again, we're not going to solve it outright. 1 over r times negative h bar squared over 2 mu times that chunk, d by dr, r squared, d by dr, capital R, plus, I'm just going to simplify no, let's do that. Minus v dE squared over 4 pi epsilon naught 1 over r plus E r squared r equals negative constant. Now, the constant here is the same trick that we did before. If I take these two equations and I add them back together, the constant's going to cancel out, and I'll get this equation again at the top. Right? That's the special thing about the separation of variables is I essentially say I'm going to have two constants, and if I add everything back together, the constants will cancel, and I'll get my original equation back out. And I forgot this has to be equal to E psi. That's where the E comes from, right? Hamiltonian operating on a wave function returns the energy times the wave function. So this part, this top part in terms of y, we've already solved. And this r squared that I brought out, that was to get rid of this r squared here. But this part here, this we solved last time. So if you flip back in your notes real quick, you'll be able to tell me what the answer to that part is. And I hope you will tell me negative h bar. It's not going to be I this time. It's going to be mu because we brought the r squared over to this chunk. Right. So the r squared is over in the radial chunk. It'll become I a little bit later when we put it back together. But right now, it's just 2 mu, L times L plus 1. We got that from last time. And if you look at side 2 of the paper I gave you, those are the spherical harmonics that I wrote on the board last time. And we can again look and say, oh, when I've got my 0, 0, my 1, 0, my 2, 0, or my 3, 0, I notice that parallelism with the polynomial expansion. We saw that last time. So this part is solved already. What's the question? Not yet. So this constant, in this case, is going to be related to this chunk, which then we can relate to whatever variables we get here. So it's not equal to E yet, but we could now, if we wanted to, replace this whole chunk with just L times L plus 1 psi, or y, right? So we've already solved that chunk. This leaves us with this chunk to solve. And what is typically done is we do some rearrangement. Notice I can set, since I know this is the constant, this also has to be that same constant for the separation of variables to work out correctly. It's not E yet, but it's the constant. So I can rewrite this. I can do a rearrangement. When I do the rearrangement, we may or may not see things that are somewhat familiar. It's kind of a mess, as all of this is. Negative h bar squared over 2 mu. I'm going to bring that r squared back across. I'm going to FOIL this part in here. So I get 2r d by dr of the function r plus r squared d by dr squared of the function r minus ZE squared over 4 pi epsilon naught 1 over r, wrong r, 1 over little r, position r, times function r, minus E times function r. I forgot a close parenthesis there. Wait, no, I didn't. Did I? Nope, that's right. That's good, that's good. Okay, I did forget a close parenthesis there. This is all going to be equal to h bar squared over 2 mu r squared L times L plus 1 r. Now, we get back some of the things that we thought we should see. You notice I get my h bar squared over 2I L times L plus 1. Since I've already operated this, I can cancel out the y everywhere. Right? Y gets canceled out everywhere because this operation would return the same function, just one constant. And I've got this whole thing just in terms of r's. If I bring this term over to here so it's all equal to 0, we've got a gnarly differential equation to solve. And I am sure you can think about how we solve these things at this point, even though we don't actually solve it. Question?
What is E dot? I know it's like the permittivity of free space or something. Like, is that
Yes.
important?
It's a constant, you know, so it's a constant that has to do with essentially how photons move through space. There's some really interesting science around whether it's actually a constant or not when you get into quantum field theory. When you start talking about, is space actually continuous or is space actually discrete at some level? That's quantum field theory. That's like, I don't even do that, but I really want to. It seems really neat. Like a lot of the constants that we are just like, oh yeah, there's a constant there, and oh yeah, the Coulomb force is attractive. A lot of that, when you start doing relativistic quantum mechanics and quantum field theory, a lot of these constants and a lot of this stuff comes out just naturally. The same way that we're about to get an energy that we're going to be like, oh, it just comes out of solving these equations. So the way that we could think about solving this equation is the same way that we didn't solve the other equations, but we thought about it, thought real hard about it, which is to say we could, if we so desired, you know, we've got this d by dr squared, so we can expect that there's going to be some exponential term. And then we've got some 1 over r and some 1 over r squared term over there. So we can guess that we're going to have some polynomial term as well. And if we wanted to, we could become mathematicians, which I would not fault you for. I think math is fantastic. If I had more time to do math, I would probably do more math. But we solve all of that. We could do a power series expansion of our function r in terms of lowercase r and see what polynomials solve that system. And then you'll get the equations on the other side of the handout I gave you. I'm going to write a couple up on the board. There's a lot of constants buried in all of this. And again, we're going to have some L value from the separation of variables that we did before. And then also when we solve this, we're going to have some counting number n value that's going to restrict from the boundary conditions that restricts what radial parts we have. And we're going to have things like R10 is equal to 2z over a naught. That's a 3 halves. E to the power of negative z over a naught r. This would be our first function that would describe the radial behavior of an electron around the nucleus. And notice, because of the symmetry of the Coulomb force, this term, because of the symmetry of that Coulomb force, it doesn't actually matter where the theta and phi are. It's just going to depend on that radial distance. How far is it from the nucleus? Then we can also look at our 2, 0. I just like looking at the zeros because I think it gives sum inside 1 over 2 root 2 z over a naught. Three halves times 2 minus z over a naught r e to the minus z over a 2 a naught r. So again, when we do the first solution, we get no polynomial. When we do the second solution, we get some polynomial term. We get some term that this is actually going to, that's actually going to be necessary to cancel it out. But because both of these are eigenvectors of a Hermitian operator, they should already be orthogonal to each other. Right? We should be able to do a big old integral and show that if I did r10 star r20 over the bounds of 0 to infinity, I would get 0. And I should also, these should already be normalized as long as I didn't forget anything. These should also be normalized already. R30 1 over root 243 z over a naught, so 3 halves times the quantity 6 minus 4 z over a naught r minus 2/3 z over a naught r squared. So if you're looking at your sheet, I find that using rho sometimes obscures where the radius is. Rho is just like essentially a radius that's scaled by this term z over a naught. That's nuclear charge over what's called the Bohr radius, z over a naught squared. I like to write it out explicitly the first time we look at these, e to the minus z over 3a naught r. And again, I can put parentheses. So what we see here is something that's kind of interesting. If we put on our mathematics eyes and we take a look at these, each of these has an exponential term. And remembering, if we're measuring distance from the nucleus, the minimum distance from the nucleus is 0. You can't have negative distance from the nucleus. So it's 0 to infinity. So r is going to be from 0 to infinity. This exponential term at the end guarantees us that this is going to be a finite function. It's always going to crash out to 0 as we go towards infinity. So this will keep us being finite. We do have some problem as r gets very close to 0. Actually, no, because then this will go to 1. Oh, we'll be okay still. We'll be okay. It'll go to 1. It's like it'll go to infinity. No, it'll go to 1. And then we've also got some polynomial term that's going to be because of all that other junk. And if we look at this, we're going to see something that is just an exponential decay, something that's an exponential decay with an extra 0 at 2, right? Because this term could be 0 as well. So if z over a naught r is equal to 2, that would also cause a 0 point in our radial distribution, what we would call a node, a second spot where probability hits 0. And then if we look at this one, we're going to have a 6 minus 4r minus 2/3 r squared. This will have 2 nodes associated with it because the quadratic will have 2 solutions that give 0. So we're going to end up with these plots that have some exponential decay and then some polynomial plotted on top of it. And we can look at those, and I've actually got something for us to look at that. But before we look at that, What's the other part we always care about when we're solving the Schrodinger equation? Probability is super important. What are some other things? Probability. What's that? Normalization constant. That's another important thing. What else do we care about? There's a couple other things we care about. Potential energy. That's part of what gives us the Schrodinger equation, so that's super important. Averages. We could calculate averages. We could calculate average position for this. We could calculate average angular positions for these. The other thing, I think there's only one thing left. Starts with an E. Yeah, energy, right? This term E, remember, the core of the Schrodinger equation is H psi equals E psi. That's what we're always doing. We always want to find the wave functions that give us the energy eigenvalue. So, what, pray tell, do we get for an energy eigenvalue out of this whole mess? If we looked at this, if we actually went through and solved this with our boundary conditions, we are going to get a negative z squared e to the fourth mass of electron divided by 32 pi squared epsilon naught squared h bar squared times 1 over n squared. That's what we get for the energy eigenvalues using these radial terms, applying the appropriate boundary conditions from 0 to infinity. And this is where it gets really neat. So A naught, that Bohr radius, has a lot of these constants buried inside of it. But what gets really neat is if we take the charge of an electron to the power of 4 times the mass of an electron divided by 32 pi epsilon naught squared h bar squared, we get a very important number. It's going to be in terms of energy. We get something that's like 2.18 times 10 to the minus 18 joules. Does anyone remember that number? Does that number look familiar to anybody? Yes. What if I wrote it as 13.6 electron volts? Does that number look familiar? Does any 1 through 5, that number looks familiar. 1 being like, nope, totally out of nowhere. Those that you have 4s and 5s, can you whisper loudly to your neighbor what it is called, if you remember? I wrote it on the board for you in case you didn't whisper it loud, in case your neighbor didn't whisper it loud enough for you to hear. This is the Rydberg constant. This thing, from everything we've done in the last 5 weeks, we solved back something that we did the first week of general chemistry. And we are now able to look at these electronic transitions. Remember, we're not looking at vibrational, rotational, or nuclear right now. We're just looking at the electronic transitions. And I can write an equation. I'm going to erase all of this and probably regret it. But we can write very simply a difference in energy, which would be like let's call this En final minus En initial. And I can just call this, rather than calling it 13.6, we also can call it our H for the Rydberg constant for hydrogen. This is for hydrogen, so that would be when Z is equal to 1 as well. And we would get Rydberg constant 1 over N final squared minus 1 over N initial squared. I'm going to put a little subscript on this E. that you're probably not going to be able to read from the back of the room, I put delta E electronic on there. Right? This is looking at those electronic transitions, taking an electron, exciting it from one state to another state, or looking at electron falling from a higher state to a lower state, and looking at the change in energy associated with that electronic transition. Not the vibrational, not the rotational, the electronic transition. So, this is monumental for a couple reasons. Reason number one, Rydberg wrote his equation for the relationship of how this works before quantum mechanics. He just did it straight from observing like hydrogen emission lamps and kind of just measuring lines and saying, oh, I noticed that it's a 1 over n, a difference in 1 over n squared. No idea how he came up with that. Must be really good with mathematics to recognize a difference in 1 over n squared pattern. But did, and was able to calculate some numerical value for this. He did it in inverse meters, is something like 1.07 times 10 to the 7 meters, inverse meters, some weird number. We could relate it to wave numbers. That's going to come up later on. But we could take this, when quantum mechanics came along, it was like, this should be one of the things that we can absolutely, and Rydberg, when he did this, had no explanation for why it was 1 over n squared. It was just, that's what he measured, right? He was able to observe, but not explain. He was able to observe, he was able to describe, he wasn't able to explain. Over the next 20 years, quantum mechanics came along. What we just did in 5 weeks took, a couple decades for most people to first figure out. So if you're like, wow, this seems really hard, it took decades for this to get first figured out. But when they went through and did all the calculations by hand without calculators or computers, they actually got the same numerical values for the Rydberg constant, and were able to explain where this 1 over n squared term comes from by restricting what their n values are allowed for with the different radial equations. So that's kind of incredible. This is one of the first things that quantum mechanics was able to give an explanation to that had already been observed and had already been seen, but not explained. So that's pretty incredible. There's a couple other things we want to talk about that were mentioned. I'm going to make a list so I don't forget. So we can show that they're normalized. We can show that they're orthogonal. We can look at probability distributions. And we can look at average values. A lot of these, this is one of those places where it'd be great if I had a worksheet to hand out and I could just be like, do a bunch of integrals, do a bunch of derivatives. But at this point, we should be comfortable looking at this and saying, yeah, I could do that if you really wanted me to. However, proving that R30 is orthogonal to R20 does not look like fun. It is going to be, especially because notice, if our bounds are 0 to infinity, we don't have symmetric boundaries, you can't use the odd integral trick. So you actually would have to do all of these integrals, keeping in mind the people who originally did this did it without computers. So we could show that these constants out front are the normalization constants, and that if we take this, well, let's write down the equations that we would look at. So the things that we would look at if we wanted to do all of these things, just as a reminder, right? Because this is really, we're doing all of the same stuff. We've defined a new potential, like we saw with particle in a box, and then we saw with harmonic oscillator, and then we saw with rigid rotor. Now, with the Coulomb force, we've defined a new potential to solve. And we can do the same things we've done for all of those. Oh, that's a weird thing. So we can do the normalization. I can say that n squared integral r1 0 r1 0 dr. Oh, I got to look back at my volume elements to make sure I get the right volume element for the r part. I think it's just dr. Double checking. It is just dr. From 0 to infinity is equal to 1. Solve for n. I think that's already been done, but we can do this for r1 0, r2 0, r1 r2 1, r3 0, r3 2. We could do it for all of the functions, right? We could do that over and over again. We can prove that they're orthogonal. Again, we have an n squared out there. We just don't care about it that much because we want this integral to be 0. We'd be looking at an r1 0, r2 0. Again, complex conjugate. These functions are real, but I still, one of the common mistakes on the midterm was people just squaring and not taking complex conjugate. So always complex conjugate. dr equals 0. Prove integral. Prove the integral is 0. Right? That's another thing we can do. We've done that quite a bit. Probability distribution would just be plot r1 0 star r1 0. Right? And we can look at that probability distribution. And the thing that we're actually going to do in just a moment is calculate average values. Zero to infinity, r1 0, r hat, r1 0, dr. Right, so those are the 4 things we could do. Question, yeah?
When we're looking at orthogonality, the normalization constant is going to be different for R1 and R2, right?
Yeah, and it's also not going to matter because the integral should be 0, right? So we can just divide that n squared over and it's going to disappear.
Is there any case of having the 2 R functions?
So just to be clear, we should have, you're right, we should have n1, n2 for the normalization 1, normalization 2, but they're not going to matter. So you are right. That's how it should be written. And that's where we've gotten a little bit lazy with our normalization constants in the past, is because when we've proven orthogonality, it doesn't matter if it's normalized or not, because you're just showing that the integral is 0. Other questions? Yeah?
What about for the averages? Does the normalization constant matter?
Oh, yeah. So here, the normalization constant matters a lot there, because if you don't normalize it, then you're not dealing with something that's fixed to 100% probability.
For
Yeah.
that same one, don't we still use the complex conjugate?
Yes, we do. Thank you. I got to be careful. So, let's see if I can make this thing work now. So, this will be a little bit boring for the video, so last time we talked about computer simulations, and man, I forgot how much I enjoy doing this stuff. So, if you can't see, you might want to move around a little bit. I've been doing things in Mathematica. It took me about an hour and a half to do the harmonic oscillator problem. I did it while MATLAB was updating in Mathematica. I still need to do it in MATLAB, but I can show you what my code looks like for that. So if you take a look, I thought I would be able to share it on your screens, but I'd have to plug it in, and that computer doesn't have Mathematica on it. So what we've got here is something that clears all the variables. I define my R0. This is my rho. So on your equation sheet, you got the rho. That's the 2z r n over a. I define my psi r function. And this function, these r's that I wrote down, this is essentially some constant out front that's based on that rho term. It's then these polynomials are called Laguerre polynomials. They are different than the spherical harmonic polynomials. A different French mathematician figured out this differential equation, so it's got a different name and a slight difference to the polynomials. But again, still has that kind of pattern of being a polynomial. And then the exponential term at the end there. Just to make this simple, I set z equal to 1 and 8. So I said charge of the nucleus is equal to 1. I set the Bohr radius equal to 1 just to make it a little bit more simple. And then I can go ahead and I can plot the different probability distributions. So right now what's plotted is the n equals 1, L equals 0 case. And we've got this nice kind of just exponential decay, climbs up to 1 and exponentially decays. So this is the probability distribution, and you can see right here, if you look at it, all I did was I plotted that psi r, that r function, squared. So I just plotted probability, I just plotted wave function squared. Notice I was a little bit lazy. I didn't take the complex conjugate because all these functions are real. We'll look at something else in just a moment where you have to make sure you take the complex conjugates. We can go ahead and go to the n equals 2, L equals 0 case. And so that would be plotting the R20. And you can see that range is too much. Let's cut that down to 8. That looks a little bit better. So what you can see in this case is we have this drop down to 0. That's the point where this internal polynomial is equal to 0. We can see that happen. We've got our exponential decay kind of plotted on top of this r climbing. So we've got an exponential decay on top of an r climbing with that extra 0 point at the 2. So we've got the 2 minus r, and then once r gets bigger, it starts taking up again. But the exponential decay wings out, so it still crashes out to 0. We can look at any value we want now. So you could shout out any n value and L value, and we can plot it and see what it looks like. Someone pick an n value.
3.
Someone pick an L value.
2.
Okay, that one's. Think back. Do you know what this is going to look like? So if we look at your equation sheet, actually, that page I gave you. Look at the n equals 3, L equals 2 case, and see if you can discuss with your neighbor what the probability distribution is going to look like just based off that functional form.
Not sure I understand the pattern yet.
So let's see. I gotta look at it too.
1, 0. And
So if we look,
0. So it went from
so
2 to
well, no, just look at this. So
yes.
you'll notice that it's a rho squared versus an e to the r negative r. So we've got like an r squared growth versus an exponential decay. We don't have a polynomial in the n equals 3, L equals 2, so we're not going to have any extra nodes. And so now we can go ahead and plot it. I might have to change the range. Yeah, I got to change the range. Ooh. That's not what I was expecting. Did I define something wrong? Hang on a second. Nope. That is not what I was expecting for n equals 3, L equals 2. I think I have a mistake in my code someplace. Psi squared. What'd I forget? Oh man, I'm so disappointed in myself right now. Which part did I forget? Let me see something real quick here. So I'm going to do a quick check. I'm going to just say, what is psi r of 3, 2? So ooh, that's not right. That's 3, 0. Okay. So I had some trouble with the Laguerre polynomials earlier. It was not giving me what I was expecting. And I don't know what's happening with these definitions of the Laguerre polynomials. Oh, I know what it is. There we go. Okay. So it has to do with the way that the Laguerre polynomials are defined. Let me just check one more thing real quick. Okay. Okay, I fixed it. There we go. It has to do with the way that mathematics defines the Laguerre polynomials versus how n and l are defined. And there's different ways that people write down the Laguerre polynomials. There's the Laguerre polynomials and the associated Laguerre polynomials. And these are the associated Laguerre polynomials. So I have to have an extra subtraction in there that I forgot. There we go. So now we should really be able to shout out any value. Let me check the n equals 2, l equals 1. I want to see if I got the right thing. 2 nodes, or 1 node for that one. Okay, good. That's more what I was expecting. Okay. I had a reversal part in there someplace that I didn't mean to have in there. So now we can look at any of these. And get some functional form. Still goes up to 1, still crashes down. This is what we're looking at now is the n equals 3, l equals 0. So we end up with 2 nodes because that's going to be this quadratic one. And it decays off. Sorry for the confusion there in the programming, but so there, we can do the probability distributions. I didn't plan on this, but let's go ahead and look real quick at how we could integrate these. Let's say av r is equal to, so the axes on this are essentially amplitude versus r. So magnitude versus r. Yeah, so the x-axis is, the horizontal axis is r. It's the safe way to say that. So what we can do is really quickly, if we wanted to do this, we could say n, l. So I can just say the average r is equal to the integral of psi r over r from 0 to infinity.
So the nodes are not allowed.
Yeah, so the nodes are places where you have 0 probability. I want to do that before that. Oh, and I forgot something. So in my equation, you're going to have psi r squared, but you're also going to have r times psi r squared because you've got to have that r operator is just like the x operator, it's just multiply by. And I have a typo someplace. Did I spell integral wrong? Oh, it's integrate, not integral. Syntax. So 45 divided by 4 would be the average radius. And if we look at this plot, 45 divided by 4 should, and keep in mind this is setting the Bohr radius equal to 1. This is setting the nuclear charge equal to 1. This means we're setting Planck's constant. We're setting Planck's constant, the reduced Planck's constant, mass of electron, and charge of electron all equal to 1, just to simplify the code. But you can see if we looked at the average position, if we look at this curve, right where I put the mouse, the average position is probably going to be, if I took like all of this, the average is going to collapse to someplace near 10 or 11. So if I take an average, I can find that. And then we could change that for any and an L value again. So if I do the 1, 0, you get 9/4. Let me think about it. It should be 2. Oh, these aren't normalized properly. Darn it. So how do I know these aren't normalized properly? I know what the answer should be for the n equals 1 case, and it's not 9/4. So the equations that I have in my code aren't normalized properly. And you notice in my code, I don't have the 2 z a naught term out front or the 1/√2 term out front. So that's the part that I'm missing in my code. That's why I'm not getting the right answers there. So when you're working on your code, make sure you're including normalization constants. Make sure you're including the correct, you're only doing probability plots, so you don't need to worry about having like average values. But you could calculate average values as well if you wanted. Just toss in another integral. Yeah, but that's why that's not working out correctly. Let's go ahead and do the average position on the board together since it's wrong in the code. What's that? The nodes are not anti-bonding. That only happens when we start putting these things together. I don't want to do anything too complicated, so I'm just going to do it for the R10. I'll leave you to do the R20 and R30 average position at home for fun in your spare time. So, let's see here. This is the integral I want to do. Oh, you know, before I talk about doing this integral, I actually want to do this integral not just for the R part, but if I wanted to know the actual average R for hydrogen, I would be looking at the integral over all space psi star r hat psi d tau. Where I have to remember, and I erased it, but we have to remember that our psi is that R part and that Y part from last time. So when I do this, I should include the R part on the front side of that equation sheet and the Y part that's on the back side of that equation sheet. I'm going to do this for the for n equals 1, L equals 0, m sub L equals 0, the kind of simplest case. And when I start plugging that all in, I'm going to get a triple integral. That is going to be R10 times R. Wait, let me see here. I got to write this a little bit different. My multiplications look too much like stars. R10 star R R10 times Y10 star Y10 R squared sine theta dr d theta d phi. dr is going to be on the integral from 0 to infinity. D theta is 0 to pi, and d phi is 0 to 2 pi. Right, and again, this is the part when we're looking at these spherical functions, or are any of those rotational parts. That's where that star becomes really important, because these y functions could have imaginary parts in them. The one that we picked here does not have any imaginary parts in it, but those could have imaginary parts. So what we're going to do, if we're going to do this, we need to make sure we're using the normalized wave functions, which are the ones you have. And we can split this up, right? This part only depends on r. This part depends on theta and phi, so I can split up my integrals a little bit. And I can say my average r is going to be equal to the integral from 0 to 2 pi, the integral from 0 to pi, y10 star, y10 sine theta, d theta, d phi, times integral 0 to infinity, r10 squared. And here I'm taking that shortcut of recognizing that those radial functions are all real, so I don't need to worry about the star part. And I'm just doing r10 squared, r squared dr. Taking that correct volume element, since I'm doing it now in three-dimensional space, I'm going to end up with that r squared term from the theta and phi part, and I'm going to bring that along with my dr portion, doing the proper integral in three-dimensional space. So the first thing that we can realize is if we're using the properly normalized spherical harmonics, this double integral at the front, y10 star, y10 sine theta, d theta, d phi, that whole thing's equal to 1. Right? And that's part of what's really nice about using orthonormal wave functions. A lot of our integrals are equal to 1, and a lot of our integrals are equal to 0. This case, though, since we've got that extra r term, that one's not going to be as simple. So we're going to have average r. I'm going to go ahead and plug in our definition of r10 and square it as well. I'm going to have r cubed. I'm going to write this in two parts, actually. R cubed, I'm going to have for a not need that normalization constant out front, the thing that I was forgot in my code. Had to have your normalization constant. In this case, you'll notice I dropped the z. We're just doing this for hydrogen, so z equals 1. And this is the normalization constant. This is that constant squared, r cubed. And I'm going to show something else because this was another common mistake. Actually, this one wasn't the common mistake, so I'm not going to show that part. 2z on a naught. Actually, I am going to show it. Z on a naught r times e z on a naught r. Oop, dr. A common mistake on the midterm was combining exponentials and doing some kind of quirky things when you're combining exponentials. Some people, when they're combining the exponentials, they were multiplying them together. Some people were factoring out things early and not really getting that correctly. So essentially, when I'm multiplying these two things together, I just add the exponentials together. So I'm going to have a negative z a naught r plus a negative z a naught r. When I add those together, I'm just going to get a negative 2 z on a naught r. This was, again, one of those situations where when you're looking at the y10s, when you were doing the normalization for the particle on a ring, people were not canceling their exponents. The exponents, and you end up with an e to the 0, but people weren't getting that. So we can look at that as well. Yeah. This integral is hopefully on your integration sheet. If you look at your integral, I forgot to check this beforehand to see if it is on your integration sheet. Not on your wave functions on your integration page. Oh yes, the x cubed is in the first column. So we can solve this using the integration table.
No, we don't.
No, we don't have it.
Yeah.
Actually, I can erase that z as well because z is equal to 1. You don't have this integral?
No.
You have the r squared?
And this one's
Oh,
symmetrical.
yes. Okay, so this one you can do this. You can do x to the n e to the ax and say a is a negative constant. So you can do this one. If you look on your equation sheet, it's that bottom is x to the n. It's x to the n times e to the ax. Where in this case a is some negative constant. A in this case would be -2 over a naught. And you can still do this integral. If we do it with the correct normalization constant out front, you should get 2/3 a naught. That is the average radius for the 1s electron in the hydrogen atom. Now, I do want to show you something else on the computer just because I did prepare for this. And I think there are other fun plots. Well, you want the one that has the a term in front of it as well, so you can carry that a through. So, the other thing that I got in my code, I thought it would also be fun to do the probability distributions of these y functions, because we didn't look at that last time. I wasn't excited about doing code at that point. Now I'm really excited. I'm like, how many MATLAB assignments can we do? I think 2. I think we can do 2. If you watch, again, if you want to come look at the, oh, that's the wrong code. That's your assignment. Don't look at that. Hydrogen functions. Here we go. So we can also do spherical plots. So here I'm just defining, again, I'm not normalizing these. I'm just looking at them in terms of plotting the spherical harmonics. And I can plot for any of the m sub l equals zeros. I can plot it. So this is the spherical harmonic for the, let's see, this is the L equals 1, M sub L equals 0. You get something that's on the order of cosine theta. And you get just a perfectly symmetric circle. If I do that instead for the 2, 0. Oh, that is the wrong one. Huh, let me think about that. Oh yeah, you know, that does make sense. 1s, 2s. Okay, that's changing the n value. So yeah, this would always be your s. This in the case where L equals 0, where we get this spherically symmetric case. That's historically called the s orbital. Now, if we wanted to do, and notice what I'm plotting here. Huh. I should be. That's funny. Let me check something real quick. That shouldn't change the answer. Ooh. Huh. Okay, so the thing that's interesting that we haven't talked about is how you can combine. If you look at L equals 1, M sub L equals plus or minus 1, you get imaginary parts in that case. And you get imaginary parts in terms of theta and phi. If we want to put this into an x, y, z coordinate system, we're going to take linear combinations of those. And now that I'm looking at the time, we'll talk about this next time. But what you'll see here is I'm taking like the spherical harmonics of the 1, 1 spherical harmonics and the 1, minus 1 spherical harmonics. I'm taking linear combinations of them. And if I plot them, I get these funny little like nobular things pointing in different directions. So that's px and py. We'll talk more about that next time. I'm going to go ahead and stop the video so we have a little bit of time to talk about midterm stuff.